Welcome back to Tech Talk Today, where we delve into the intricate world of technology and data management. I'm your host, Your Name, and today we're exploring partitioning schemes in databases, focusing on key value data models and their approach to secondary indexes. So grab your headphones and let's dive in. To start, let's break down the basics of partitioning in databases. Essentially, partitioning involves dividing your data into smaller, manageable pieces, or partitions, which helps improve performance and scalability. In many databases, especially those using a key value model, records are primarily accessed through their unique primary keys. This straightforward method makes it easy to determine which partition a record belongs to, allowing for efficient handling of read and write requests. But what happens when we introduce secondary indexes? These indexes are vital for searching data that doesn't rely solely on primary keys. For example, if you want to find all actions by a specific user or all articles containing a certain word, secondary indexes are essential. They enable you to search for occurrences of values across your dataset, which is crucial for both relational and document databases. Now, things can get a bit complicated here. Many key value stores like HBase and Voldemort have traditionally shied away from secondary indexes due to their complexity. However, some, like REAC, have recognized their importance and begun to implement them. After all, secondary indexes are fundamental for search servers like Solr and Elasticsearch. Let's visualize this with a practical example. Imagine you're running a website for selling used cars. Each car listing has a unique ID, and you partition your database based on these IDs. For instance, IDs 0 to 499 might go into partition 0, while IDs 500 to 999 go into partition 1. But what if you need to search for cars by color or make? This is where secondary indexes come into play, allowing you to quickly find all red cars or cars from a specific manufacturer. When you add a red car to your database, the system automatically updates the secondary index for color, linking it to the appropriate document ID. Each partition maintains its own secondary indexes, which only cover the documents within that partition. This is referred to as a local index. In contrast, a global index spans all partitions, but requires careful partitioning to avoid bottlenecks. For example, you might partition the index by the term itself, like color, red, or use a hash of the term. This term-partitioned approach can enhance read efficiency, as it allows clients to query only the relevant partition. However, while a global index can speed up reads, it complicates writes. A single document write might impact multiple partitions of the index, potentially slowing down the process. So, it's crucial to weigh the benefits of faster reads against the possible drawbacks of slower writes. Now, let's shift gears to rebalancing partitions. As your application grows, you may need to add more resources, such as CPUs, disks, or memory. When this happens, data and requests need to be moved between nodes in the cluster, a process known as rebalancing. Rebalancing comes with some key requirements. First, the load should be evenly distributed across the nodes after rebalancing. Second, the database must continue to accept reads and writes during this process to minimize disruption. Lastly, you want to move as little data as possible to speed up rebalancing and reduce the load on the network and disk I/O. Let's briefly discuss how partitions are assigned to nodes. One common method is to partition by the hash of a key. While using a modulo operation to assign keys to nodes might seem straightforward, this approach can lead to excessive data movement when scaling. For example, if you start with 10 nodes and later add more, many keys will need to shift to different nodes, making rebalancing costly. A better strategy is to assign several partitions to each node from the beginning. This way, you can distribute the load evenly and avoid frequent data movements. When a node is added or removed, only entire partitions are transferred, which minimizes disruption and keeps the system running smoothly. Now, let's touch on fixed versus dynamic partitioning. Many databases begin with a fixed number of partitions, which simplifies operations but can be limiting. If you set your partitions too low, you may face performance issues as your dataset grows. Conversely, if you set them too high, you'll incur unnecessary overhead. Dynamic partitioning allows databases to adjust the number of partitions based on data volume. For instance, in key-range partitioned databases like HBase, partitions can split when they exceed a certain size, ensuring a balanced load. This flexibility can significantly enhance performance and simplify rebalancing. However, dynamic partitioning has its challenges. When a partition grows, it can be split, and if data is deleted, it can merge with an adjacent partition. This process helps maintain a manageable size for each partition, which is crucial for efficient rebalancing and recovery from node failures. In summary, whether you're utilizing local or global indexes, or fixed or dynamic partitioning, the goal is to optimize performance while ensuring data integrity and accessibility. It's a delicate balance, but grasping these concepts can help you design a more efficient database architecture. That wraps up our exploration of partitioning schemes and databases. We've covered a lot, from the fundamentals of key value models to the intricacies of secondary indexes and rebalancing strategies. Remember, choosing the right partitioning approach can significantly impact your database's performance and scalability. Thank you for tuning in to Tech Talk today. If you enjoyed this episode, don't forget to subscribe and share it with your friends. Until next time, keep exploring the fascinating world of technology. I'm your name, signing off. See you next time.